Welcome, dear students, once again after a long time. And once again, we are going to start with topology. And today, we are going to start with filters in the chapter Nets and Filters. So, I'm going to start with this chapter Nets and Filters. There are several videos on my YouTube channel based on nets. And today, I'm going to start with filters. So, let us see what is the definition of a filter. Just like you studied topology in the starting, you studied the definition of topology, the definition of filters is also very similar and is very easy. So let X be a non-empty set. Let X be a non-empty set and Px be the power set of X. Power set of X means the set of all subsets of X. Then F, subset of power set of X, that means collection of subsets of X, is said to be a filter on X, is said to be a filter on X if it satisfies three conditions. And what the three conditions are? The first condition is that phi should not be there in F. That means this F is a proper subset of X. It does not contain phi. Secondly, if a particular set F belongs to this family F and H is a superset of F, then H also belongs to F. That means once a set belongs to F, all its supersets must also be there in F. And the third condition is if F and H are two members of F, then their intersection F intersection H also belongs to F. That means we are talking about finite intersection. If any number of members you take from the family F, that means F1, F2, F3 and so on, Fn, finite number of members, then their intersection F1 intersection, F2 intersection and so on up to intersection Fn, that must also be there in F. If these three conditions are satisfied, then this collection F of subsets of X is said to be a filter on X. So this is the basic definition of filter, what a filter is. Now let us see some properties of filters and then we'll move on to some theorems of filters. First thing, it is clear that let F be a filter. Since this F is a non-empty collection of subsets of X, definitely at least one member will be there in this set. So let F be a member of F, and this F is a subset of power set of X. That means this F is a subset of X. And since this F is a filter, by the second property of definition of filters, F belongs to filter and F is contained in X, that means X is a superset of X. By the second property, X must also be there in the filter. So it is, one thing is clear, that if F is a filter on X, then X must be there in the filter. So it is very trivial property of filters. Another thing is to be noted that power set of X itself is not a filter. Why? Because it contains phi. And in our definition of filters, phi must not be there in filter. So this Px, the power set of X itself, it is not a filter. Another thing, if F is a member of filter, then definitely its complement must not be there in the filter. Why? What is the reason? The reason is very trivial, very simple. Suppose F and F complement both are there in filter. Suppose, if possible, F is in filter and F complement is also there in filter, then in the definition by third property, F intersection F complement must also be there in the filter if both these belong to filter, and F intersection F complement is phi, so phi belongs to F, and this is a big contradiction because in the definition the very first condition is that phi must not be there in F. So if F is there, F complement cannot be there in the filter. So it is another useful thing that we will use while we will prove some theorems based on filters. And then another thing is there are two basic definitions. One is free filter and another is fixed filter. Fixed filter and free filter. We have seen that finite intersection of members of the filter is always non-empty because of the third property of the definition of the filter. But what about the arbitrary intersection? Arbitrary intersection of members of a filter, it may be phi, it may not be phi. If arbitrary intersection of members of a filter is phi, then it is called free filter. And if arbitrary intersection of members of filter is also non-empty, then it is called a fixed filter. So these two things are very important. Once again, we will use these two definitions while proving theorems and while moving on to the further topics of filters. Now we are moving on to the types of filters. Similarly, what we did there in the definition of topology, indiscrete topology, discrete topology, Sierpinski topology, neighborhood topology, several topologies, types of topologies are there. Similarly, there are some types of filters. So first of all, there is indiscrete filter. In the topology, we had indiscrete topology. And what was indiscrete topology? Indiscrete topology was the topology containing the set phi and the set x itself. It was the indiscrete topology. And if we relate topology to the filters, in filters the first condition is that phi should not be there. So this phi should not be there. So what we have only the singleton set, and this singleton set X is called indiscrete filter. It is a filter. Without any doubt, it is a filter because it is a non-empty collection of subsets of X. The first thing, phi does not belong to this filter, and it contains only X. There is no superset of X because it is a filter on X. So second condition is clear. Third condition, it contains only X, and X intersected with itself is always X, and it belongs to this set, this collection. So this is a filter known as indiscrete filter. Now another type is cofinite filter, which is very much similar to the definition of cofinite topology. Let X be a set, and better if you take an infinite set, because we are talking about the cofinite filter, you can take infinite set, but it is true for all sets, because if it is a simple set, then one thing, then there may be a problem because the complement of X is also finite, so we will have to take here infinite set. Let X be an infinite set, then the collection F containing those subsets of X whose complement is finite is a filter known as cofinite filter, and we will prove that it is a filter. The proof is very easy. The first thing, phi does not belong to it. What is the complement of phi? Complement of phi is X, and this X, we have taken X as infinite set. So phi complement is infinite. Phi complement is infinite. It is not finite. If its complement is finite, it is a member of F. Since phi complement is not finite, it is infinite, so phi does not belong to F. So first condition is clear. Secondly, let F belongs to this family and H be a superset of F. Now F belongs to this family. If F belongs to this family, then F complement is finite. So this means F complement is finite. And H contains F. Taking complement on both sides, you will get H complement is a subset of F complement. Now H complement is a subset of F complement and F complement is finite. So subset of a finite set is always finite. So this means your H complement is finite. And since H complement is finite, your H belongs to F. So this means your H belongs to F. And it means the second condition is satisfied. If F belongs to F and H is a superset of F, then H is also there in F. So second condition is also satisfied. Now we move on to the third condition so that we'll prove that it is a filter. Thirdly, let F and H be two members of this collection. This collection contains those sets whose complement is finite. So that means F complement and H complement are finite sets. These are the finite sets. And we know that if two sets are finite, then their union is also a finite set. And by De Morgan's law, you will get F intersection H complement is a finite set. And since complement of this set is finite, this set must be there in the collection. So this means your F intersection H belongs to F. You have taken two sets F and H from this collection and their intersection is also there in F. That means the third condition of the definition of filters is also satisfied. So this collection becomes a filter and it is known as a cofinite filter. Okay, now we will move on to the next type of filters on a set X. Let us see which one it is. Just now we have seen that if X is infinite, then the collection F subset of X such that F complement is finite. Just now we have talked about this filter. Here if I replace this X with the set of natural numbers n, then one thing is clear, then n is an infinite set. So this filter can be defined. Okay, it is a cofinite filter, but particularly this is called a Frenchy filter. This is called a Frenchy filter if in the definition of cofinite filter you replace the set X by the set n of the set of natural numbers. So it is another kind of filters on X. And then there is neighborhood filter. Neighborhood filter, very much like that neighborhood topology. What you have to do, X is a set given, you take any element x0 belonging to X and then nx0. nx0 means the set of all neighborhoods of x0. Then this is also a filter known as neighborhood filter. And once again, to prove this that this is a filter is very easy. We know that phi is not a neighborhood of any point, so phi will not be a member of this collection. Secondly, if F is a member of this collection, that means then what is F? F is a neighborhood of x0. And if F is a neighborhood of x0, then every superset of F is also a neighborhood of x0, so that will also be a member of this collection. Thirdly, if F and H are two members of this collection, then F and H will be the neighborhoods of the point x0, and we know that the intersection of two neighborhoods of x0 is also a neighborhood of x0, so their intersection will also be a part of this collection. So third condition of the definition of filter is also satisfied, so this will become a filter known as neighborhood filter. In discrete filter, you have seen that it is very much like that of in discrete topology, but in case of discrete filter, the definition is a little bit different. So let us talk about the discrete filter. So what we have to do here, let x be any set, let x not be any point of this set x. Now consider the collection of those subsets of x which contain that particular point f. That means you are to take all those sets in the collection which contain the point x0, then it will be a filter. We will prove that it is a filter, and this filter will be called discrete filter. Number one, first thing, phi does not belong to f. Very much clear, because if phi is to be a member of this collection, then x0 belongs to phi, which is a big contradiction. So that means phi will not be a member of f. So the first condition is satisfied. Now move on to the second condition. Let f be a member of this collection and h be a superset of f. Since f is a member of this collection, so x0 must be there in f. So this means x0 belongs to f, and h is a superset of f, means f is a subset of h. x0 is in f and f is a subset of h. This means x0 also belongs to h, and if x0 belongs to h, by the definition of this collection, your h belongs to f. So the second condition is also satisfied, that if f is a member of this collection and h is a superset of f, then h also belongs to this collection. Thirdly, if f and h are two members of this collection, then we are to show that their intersection is also there in this collection. Since f and h are the members of this collection, by our definition of the collection, x0 belongs to f and x0 belongs to h. Now x0 is there in f, x0 is also there in h, that means x0 is there in f intersection h. So that means f intersection h contains x0, and whatever the set will contain x0 will be a member of this collection. So this means your f intersection h belongs to this collection. So the third condition is also satisfied. So this becomes a filter, and it is called discrete filter. Another thing is to be noted that if we replace this point x0 by a subset A of x, suppose I'm not using the definition discrete filter now. Suppose x be any set and A is a subset of x. Instead of taking x0 to be a point of x, now I'm taking A to be a subset of x, and I'm taking all those subsets of x which contain A. All those subsets of x that contain A. Then once again it will be a filter. How? The first condition is very much clear. Phi does not belong to f, because otherwise A is a subset of phi, and A here is non-empty. A here is non-empty. So phi A is a subset of phi, that means a non-empty set is a subset of phi is a contradiction, so phi will not be a member of f. Secondly, if f is a member of f and h is a superset of f, then by the definition of collection, your A will be a subset of f, and f is already subset of h. By transitivity, A will be a subset of h. That means your h contains A, and if h contains A, then h belongs to f. So the second condition will be fulfilled. Thirdly, if f and h are two members of this collection, then by definition A will be contained in f and A will also be contained in h. Since A is contained in f, A is contained in h, that means A is contained in f intersection h, and that means f intersection h is also a member of this collection, making this collection a filter on x. So it is another useful filter we have defined. It is just similar to the discrete filter, but exactly not discrete filter, because in this discrete filter, what we have to take? We have to take a single point x naught and all those sets which contain that particular point x naught. Now moving on to another definition, that is comparison of filters. Comparison of filters. Let X be a set, a non-empty set. Let X be a non-empty set. Why non-empty? Because on the empty set phi there will be no filter. Why? Because if X is empty, you have to take the collection of subsets of X, and X itself is phi. So only subset of X will be the phi itself, and phi is never there in filter, so the filter will not be formed. So we will have to take X to be a non-empty set. Let X be a non-empty set, and let F1, F2 be two filters on X. If F1 is contained in F2, if F1 is contained in X2, we say that F1 is weaker than F2, or we say that F2 is stronger than F1, or we say that F1 is coarser than F2, or we say that F2 is finer than F1. Most of the time we will be using this one. If F1 is contained in F2, then F2 is called finer than F1, and this we will use in the theorems coming onwards. So let us see what type of theorems are there on this topic, filters. So let us take one theorem. We will start with some theorem. So the first theorem comes into my mind is, let X be an infinite set. Let X be an infinite set. Then let X be an infinite set, and let F be a free filter on X. Free filter on X. Free filter on X means the arbitrary intersection of members of F is phi. I'm going to write here, arbitrary intersection of members of F is phi. This is given to us now because it is a free filter. Then this F is finer than cofinite filter. That we have to prove. Now let us see how to prove this theorem. This filter F is given to us, and we are also to talk about the cofinite filter. So let us name cofinite filter as C. Let C denotes cofinite filter on the set X. That means C contains all those subsets of X whose complement is finite. And what we have to show that? We have to show that F is finer than cofinite. What we are to prove? We are to prove that F contains C, or that means C is a subset of F. We'll prove it by the method of contradiction. Suppose, if possible, F does not contain C. That means there will be a member in this cofinite filter C which will not be there in F. So therefore, there exists C belonging to the cofinite filter such that C does not belong to F. Now, C belongs to cofinite filter means C complement is finite. C complement is finite. Suppose C complement be x1, x2 and so on xn. Now x1, x2, xn, they are all members of X because both F and C are the filters on X. F is a free filter. Intersection of all the members of F is phi. Since intersection of F belonging to F is phi. Therefore, for example, if you talk about x1, then there will be at least one filter F1 which will not contain x1. Why? Because if x1 is contained in all the filters, then it will be there in the intersection. But intersection is phi. Therefore, there will be at least one filter which will not contain x1. So therefore, there exists F1 such that x1 does not belong to F1. Similarly, there will be a filter F2 such that x2 does not belong to F2. There will be a filter Fn such that xn is not there in Fn. So we are having these filters F1, F2, Fn such that x1 is not there in F1, x2 is not there in F2 and xn is not there in Fn. So that means let G be the intersection of Fi, I vary from 1 to n. That means what I am going to take intersection of these filters F1, F2 and Fn. X1 is not in F1, so x1 will not be there in the intersection. Similarly, x2 will not be there in the intersection. Xn is also not there in the intersection. That means x1, x2, xn are not there in this set, but they will be in the complement of G. This means this x1, x2, xn, they will all be, this set will be a subset of G complement. This will be a subset of G complement, and what this set is C complement. So C complement is a subset of G complement. Taking complement once again both sides, G is a subset of C. Now, what is G? G is finite intersection of filters on X, and we will prove that not only finite intersection, even the arbitrary intersection of filters on a particular set X is also a filter. So this G is also a filter on X. So G and more than G will be a member of this F, because all these F1, F2, Fn, they are members of F, so their intersection will also be there in F. So G belongs to F. G belongs to F. Now G belongs to F. F is a filter and C is a superset of G. By the definition of filter, second condition, C belongs to F. This means C belongs to F, and this is a contradiction because we have just above we have seen that C does not belong to F, and now C belongs to F. This is a contradiction, and why this contradiction is there? Because we have supposed that F does not contain C. That means F must contain C, or you can say that this filter F, free filter, is finer than the cofinite filter. So here I am going to stop this video. In the next video we will have more theorems on filters, we will have more definitions, more fundamentals on filters. Till then, thank you once again.